This is Mr. Beck Does Your Homework, question number 15. The entrance of a science museum features a funnel into which marbles are rolled one at a time. The marbles circle around the wall of the funnel, eventually spiraling down into the neck of the funnel. The internal radius at the funnel at the top is 0.44 meters. At the bottom, the funnel's neck narrows to an internal radius of 0.043 meters. A 5 times 10 to the minus 2 kilogram marble begins rolling in a large circular orbit around the funnel's rim at 0.25 revolutions per second. If it continues moving in a roughly circular path, what will the marble's angular speed be as it passes through the neck of the funnel? Consider only the effects of conservation of angular momentum, and answer in units of radians per second. Now, if you've ever seen one of these things, it looks very much like almost like a tornado sort of thing. And your objects will start spinning around the outside. Sometimes it's coins, and then slowly friction will take them down and slow them down a little bit, but they'll get zoom, 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 zoom down here before they finally fall down through the bottom. So what this is a conservation of momentum problem. So I will have some angular momentum up here as it's orbiting around, and I will have the same angular momentum down here as it's orbiting around at a much higher velocity. So just like the skater pulling in their arms, this wall of the funnel pulls in the mass and makes it orbit quicker and quicker. So since this is an angular momentum problem, I know that my angular momentum initially is going to equal my angular momentum later on. My angular momentum, just like P equals mv, L is going to equal I omega. So my initial I omega is going to be my final I omega. Now, omega is given for me initially, but the omega that's given to me is revolutions per second. So I'm going to have to convert revolutions per second into radians per second, because that's how I answer. So I've got to convert revolutions per second to radians per second. But I know that if I have 0.25 revolutions per second, then each revolution, so I'm going to do times and draw a line, I know that one revolution is going to be 2 pi radians. So that is a conversion I'm going to have to make. So this would be 0.25 times 2 pi divided by 1, and now I can get rid of revolutions, and I'll be left with radians on the top and seconds on the bottom. So that's radians per second. So that's what I'm going to plug in for my initial omega. But now I need my I. And the moment of inertia of a mass that's moving around in a circle, the moment of inertia for that mass is going to be the mass times the radius squared. So I am given the radius of the funnel up here. The internal radius of the funnel at the top is 0.44 meters. So I'm going to place 0.44 meters here for my radius. The mass is the mass of the marble, and that's going to go here. Now actually, if you pay attention, you'll see that on the right side I'm also going to have mr squared. So if I write this out, on the left I will have mr squared omega, and on the right I will have mr squared omega. Now I know that the omegas are different, so I can have this be r1 and omega 1, and this be r2 and omega 2. But the masses are absolutely the same, so I can even get rid of the mass in this equation. So I have r1 squared omega 1 equals r2 squared omega 2. And I have just solved for, using this, my initial omega. I'm given my initial r up here in meters, and I'm given my final r over here in meters. So that'll leave me solving for my final omega, as long as I remember to square.